Hello, my friends, and welcome to Origins. My name's Don Chapman. It's my privilege to be your host. You know, during our show, we showcase interesting guests who present evidence from science along with other important facts validating the truth of creation and the accuracy of the Bible. Today's guest is Dr. Jason Lisle. He is the Director of Research at the Institute for Creation Research and specializes in astronomy, physics, and apologetics. He has a PhD in astrophysics from the University of Colorado, where he made a number of discoveries relating to the solar photosphere. Dr. Lisle, welcome to our program.
Thanks for having me on.
We're going to talk about the sun today.
Yes.
It's probably something that's really more important in our lives than the time we give thinking about it, isn't it?
That's certainly true. You can't have life without the sun, at least not the way that God has designed our universe anyway, and life on our planet. We really do depend on the sun. It's an important star. It is a star. And it's something that declares biblical creation. So that's what I thought we'd talk about today.
I think that's great.
So when we read in Genesis, we read a number of purposes that God has for the lights that He made in the heavens, which includes the sun, the greater light, the moon, the lesser light, and the stars also. And we read in Genesis 1:14 and 15 that then God said, "Let there be lights in the expanse of the heavens to separate the day from the night, and let them be for signs and for seasons and for days and years." So we have separating day from night, and we have signs, seasons, days, and years. Those are all units of time that the stars, the sun, and the moon mark. And then in verse 15, "And let them be for lights in the expanse of the heavens to give light on the earth." And so they produce light and illuminate the earth. And it was so. And then we read that God made two great lights, greater in size in terms of our apparent size in terms of our sky. The greater light, that would be the sun, to govern the day, and the lesser light, that would be the moon, to govern the night. And so they govern the day and the night, and so He made the stars also. And of course, we read later in the Psalms that the heavens are telling of the glory of God, and so they reveal His glory. And so, as far as I can tell, there are at least 5 purposes that God has for the luminaries, of which the sun is one. They separate the day from the night. They determine time, or they measure time. At least,
seasons,
yeah.
Days and years,
And we can recognize time based on those, yes. And they give light upon the earth. They illuminate the earth. They govern the day and the night. They rule over it. They determine when day and night is, and so on. And they declare God's glory. There might be others too, but those are some that I think that the...
Sure, the basics.
Yeah, and the interesting thing about these things is most of these are done almost entirely by the sun.
Yes.
Because the sun is what separates the day from the night. The moon and stars don't. It's all the sun, and that particular one. Signs, seasons, days, and years, that's all of them, although the sun determines the day. It determines the length of the day. Of course, Earth's rotation on its axis with respect to the sun. To give light upon the earth, now all of them do that, but the sun does it to a much greater extent than the moon and the stars. The sun is much, much brighter than the moon and the stars. And of course, they govern the day and the night. The sun governs the day. That's it. When the sun's out, it dominates everything else in the day sky. You know, the stars technically are visible during the day. And if you have a telescope, you can see some of the brighter stars in a telescope. But the sun just so dominates the day sky that it pretty much blocks out anything else. And I think all of them declare God's glory. So, yeah. But it's interesting that of these purposes, the sun really is the greater of the great lights, and it does these functions.
Where we're positioned, it's the big dog, yeah?
It really is. Here's, of course, an image of the sun, and so I thought we'd talk a little bit about some of the characteristics of the sun and how it confirms biblical creation. The size of the sun is impressive. It is over 100 Earths across.
Wow.
If it were hollow, which it isn't, but if it were, it could hold 1 million Earths inside of it. So it's just astonishing, the size of this. And we can compare it to Jupiter, for example. Jupiter's 10 times the size of the Earth. Now, Earth is in this image. It's just below Jupiter. It's that little speck below Jupiter.
Wow.
So it just gives you a feel for how big this object
tiny
is.
that is.
Yeah. And of course you say, well, it looks so small in our sky. Well, it's 93 million miles away. And so if you were to drive at reasonable speed, 60 miles an hour, it'd take you over 150 years to drive to the sun. You couldn't do it in your lifetime. That's how far away it is and how big it is. Not only is it big, it's massive. Most of the mass of the solar system is in the sun. In fact, if you were to take a 10-pound bowling ball, that would represent the mass of the sun. Everything else in our solar system, all the other mass would be represented by a penny and a nickel. Everything else, all the planets, all the moons, all the comets, all the asteroids are the penny and the nickel. In fact, the nickel is Jupiter.
Everything else is the contrast,
yeah. So it's phenomenal. So the solar system is mostly the sun. The sun is a star. And that in itself is interesting, and it's not something that people knew until a few hundred years ago when people started thinking, you know, those little points of light that we see, those are the same type of thing as the sun. They're just much, much further away. and the sun is the one that's much closer to us, and we orbit the sun, and so it seems to change its perspective relative to the stars. It is a main sequence star. Now that's a particular type of star of which most stars are. Most stars belong to what's called the main sequence. And the way you can see this is by plotting the brightness of a star versus its temperature, which is indicative of color. The cooler stars are red, the hotter stars are blue. And so if we plot this, you'll see that the stars fall along this curve, which we call the main sequence. Most stars do that, and the sun is right there on that main sequence, and so that it actually belongs to the main sequence. It obeys a rule that if you know the mass, you know everything else about the star. You know its brightness, you know its size, you know its luminosity, everything about it. The sun obeys that rule, and so it falls right along that line. By the way, they used to think that that curve was an evolutionary curve, that the blue stars evolved into the red stars, and now everyone agrees that's not the case. It just shows you how secularists, a lot of times, they want to jump on an evolutionary explanation for things.
And they backtrack.
Yeah, and then sometimes they don't. But my point is, it prevents finding out what the real scientific answer is to that sequence. We now know it's a mass sequence. It has nothing to do with time. Those stars are different masses. The ones on the left side of the curve are more massive than those on the right. Then you have a few stars that are off main sequence. They're giants and supergiants and so on. The sun's designed for life. It's at the right distance from the Earth so that we can receive the proper amount of heat and light, and that's very important. The sun has the right temperature, mass, and luminosity for life on Earth. It turns out if you were to dial up the sun's temperature, it of course would be hotter, it would be bluer. Now you could say, well, that's no problem, we'll move the Earth further away, but it's still a problem because if you move the Earth further away so that the temperature's right, the Earth's still getting a lot of ultraviolet radiation from a blue star. Blue stars put out a lot of ultraviolet radiation, which is dangerous for life. And so, in fact, the sun puts out a little bit, and that's what causes sunburns. You know how that can be a bit of an issue. If the sun were a blue star, it would make life very, very difficult. And of course, if it were a little red dwarf star, you'd have to put the Earth much closer to it, and then you wouldn't get as much light per unit heat. The sun's optimal in terms of its mass, its luminosity. It's the right type of star, being a main sequence star, the right mass, the right luminosity, and so on. Some stars have what are called super flares, where they release enormous blasts of radiation that would just destroy life on Earth. If the sun did that, the sun doesn't do that. It has relatively mild flares. So it's just the right type of star. It's at the right location in our galaxy, not only for life to exist, but for us to be able to do science, which is interesting. If the sun
almost
were,
like a platform we're on, isn't it?
It is, yeah. And in fact, if the sun were right in the middle of the galaxy, or maybe in the middle of a globular star cluster, it would be very spectacular, but it'd be hard to see beyond it and see the rest of the universe. We're kind of in a location where we can see the other stars in our galaxy, but we can also see out of our galaxy. And so it's in the right sort of location in the universe for us to be able to do science.
When you first look, it looks like we're just down in the corner, but the more you study it, then it seems like God positioned us there so that we could look and study.
Right. That's right. There's a reason God put us in the suburbs of our galaxy.
And there's no question that all of that is so fine-tuned to support our life.
Exactly.
Yeah.
And I thought we'd take a look at the sun now. I think we'll go up to the screen and we'll have a look at some of the anatomy of the sun. And so you can see here the main properties of the sun. This is what the sun would look like if we could cut it open. You have the outer visible surface that you see is called the photosphere. Now, of course, you don't want to directly look at the sun, but with protection, with certain visors, you can do that safely. And then you'll see, that's what you see is the photosphere. But if we go into the sun, the center is the core. We think it's about 15 million degrees Celsius in the core. So it's very, very hot there. And it's so hot that the hydrogen is actually slammed together and produces helium. And so that's actually the power source for the sun, the hydrogen being converted into helium. And it's got enough hydrogen gas that they could do that for a lot longer than humans will have to worry about it. And so then outside the core, you have the radiative zone where the energy kind of moves out rather gently. And then you have the convection zone. And the convection zone is where you have these large motions where the energy from below gets moved up to the top, and it's distributed that way. And then on the top of the convection zone is basically the photosphere. You're looking at the very top part of the convection zone. Above the photosphere, there are these quasi-invisible layers that you don't normally see called the chromosphere. You can only see that with your naked eye during a total solar eclipse when the photosphere is blocked, and then the much fainter chromosphere becomes visible. And it's very colorful, which is why it's called the chromosphere. And then beyond that, you have the corona. The corona is these outer layers, and it actually extends out a little ways into space. It's like a real thin, very tenuous sort of atmosphere. Now, the sun is basically a ball of gas, but it's interesting that it's organized in this way, that it has these particular properties. And at the University of Colorado, where I did my PhD work, I studied the photosphere. And of course, you're looking at basically the top of the convection zone when you're looking at the photosphere. And I studied how things move on the photosphere of the sun. And it was a lot of fun. It was really a neat project. If we were to take a look at the surface of the sun close up, this is what you'd see. And I think it's amazing that we have instruments that can do that now. This pattern that you see here is called granulation. Each one of these is a granule, and that's where you have material coming from the inside, and it kind of bellows up, and then it kind of goes back down and sinks down in these downflow lanes. So it's kind of like a beehive pattern, an irregular beehive of convection, of motion coming up from the interior and then being distributed that way. And there are other scales of convection too. There are mesogranules, where they're a little bigger than granules, and then supergranules, which are about the size of the Earth. And then you have these giant cells, which are even bigger yet. And in fact, my research actually I was the first to see actual evidence of giant cells on the surface of the sun.
Wow,
so
that's
it's
awesome.
quite exciting. Yeah,
Jason.
it's pretty neat. So I'm a creation scientist, and I've made discoveries in science because of that. We take a look at granules, though. Granules you can see directly. They're about, each one of these, just to give you a feel for it, each one of these is about the size of Texas, just to give you a feel for it.
They're not little tiny things.
They're not. They look like it, but that's only by
right.
contrast. If we zoom in on them again, you have a nice clear image of these different granules, which we can use with various instruments, both on Earth and in space. In fact, I actually used the spacecraft in my dissertation research, the SOHO spacecraft, and it now has another one that's its successor, and it's able to get even higher resolution images. So it's really quite fascinating. Here's what the sun would look like to the naked eye. Again, if you use protection, you don't want to look right at it. And you can see a number of features. You can see, first of all, let me point out, it's darker along the edge. Have you noticed that? It's called limb darkening. And the reason that is because the sun is a ball of gas. And so when you look at it, you can actually look into it a little bit, because it's like a fog. You can see a little ways into it. And when you're looking right at the center of the sun, you're looking into the interior where it gets hotter and is therefore brighter. Whereas when you look along the edge here, you're skimming along the surface where it's a little cooler. And that's why you get that limb darkening. And so we think other stars would do that as well, although we don't have good images of other ones.
Is that a coffee stain on it there?
You can see there a little spot right there. And they call that a sunspot, because again, astronomers aren't very creative, but those tend to happen on the sun. And those are caused by magnetism. You get a strong magnetic field that will inhibit convection. It prevents energy from coming up from beneath. And so that area is cooler than the rest of the sun, and which is why it is fainter. It's not as bright. The surface temperature of the sun is about 6,000 degrees Celsius, whereas these sunspots are a chilly 4,000 degrees Celsius. So they are a little bit cooler. And you can see even at this scale, you can see barely that granulation. You can see that there just on the really small surface there. If we zoom in on these sunspots, you can see the granulation and the sunspots there together. And it's really interesting. And of course, I studied how the magnetic fields, of which this is just an enormous magnetic field that's causing that. And you can see it disrupts the pattern of the granules around it. So it's really quite fascinating. Just to give you a feel for the scale, there's Earth compared to the size of a typical sunspot. Yeah.
So the Earth isn't even as big as the spots.
Well, some of them. It's a little bigger than some of them, and it's smaller than others.
Yeah.
So it's astonishing how big this is. Now, how do we know what we know about the composition of the sun? Most of what we know about the composition of things in space is done through a field called spectroscopy. And this is just a fun area, because sometimes it's good to ask, how do you know that that's true? Because sometimes they don't really know what's true. Well, it turns out if you take the sun and break its light into a rainbow, basically, and you do this very precisely, you'll find that there's these little black lines in the solar spectrum, and those are basically an atomic fingerprint. They're telling you what the sun is made of.
Wow.
And of course, it was Fraunhofer who mapped these very accurately. There were 9 very thick ones, and then there are these much finer ones as well. And these are like fingerprints of different types of atoms that make up the sun, basically. And some atoms will have different lines and so on. And we know this because we can do this in a laboratory. We find that certain atoms, when you heat them up, will give off these characteristic fingerprints. There's hydrogen, for example. It gives off those characteristics colors, or it can absorb them depending on the situation. So they'll be either black or bright depending on the situation. Helium, lithium, oxygen, and so on. Some of them, and these are caused by the different electron levels that exist within an atom. And so this is how we know what the sun's made of, because we found, for example, that hydrogen, the sun is mostly hydrogen, and if we take the hydrogen spectrum, lo and behold, it matches right up with those black lines on the sun. So that's how we know what the sun's made of. In fact, there was an element that, we now know that it's got all these different elements, and there are a couple, Earth's atmosphere gets in the way too, so that adds the oxygen there. But there was actually an element that was discovered on the sun because they found a pattern for which they had not discovered any fingerprint on Earth. And so it's the sun element. And they named it after the sun, the Greek word for sun, helios. And so they named this element helium. Helium was actually discovered on the sun before it was discovered on Earth. So isn't that fascinating?
I didn't know that. That's amazing.
Most people don't. And then, of course, later it was found on Earth, and it was found to have this characteristic fingerprint, and that's how we know about that. So the sun is mostly hydrogen and helium gas. Everything else, a little bit there, but 2%. So it's a ball of gas, basically, amazingly. And of course, we can take a look at the sun in different wavelengths and get different information about it. Different wavelengths penetrate to different depths. And so when you look in this particular wavelength, the sun looks about like it would to your eye, and you're seeing the visible photosphere of the sun. Now, when we move to a different wavelength, now you can see a little bit higher up, and you can see some of these features here. In fact, you can see some of the supergranules now. The supergranules are bigger than the granules, and they're about the size of the Earth, and you can see that pattern there, and you can see the sunspots. And these light regions are called plage. The energy that's lost from the sunspots tends to get distributed around it as well. You can see here a little higher in the chromosphere. You can see this is an image here where you can see a little bit of the features that are higher up. We go even higher, you can see some of the lower regions of the corona, and we go higher still, and you can see all kinds of interesting features there as you go higher and higher into the sun, including where these sunspots would be.